This is the first lesson in a series of lessons covering the basic building blocks for IC fabrication, particularly analog IC fabrication. And this material comes from Sutter and Smith's Chapter 7 of their textbook, Microelectronic Circuits. We'll be talking about these 5 items: gain blocks, cascoding, amplifier stages, IC current biasing, current mirrors, and some useful transistor pairings. And following all this material, we will then be introduced, or it'll lead up to Chapter 8, in which we will study the differential pair, which is another useful pairing. So before we dive into these 5 items, first let's just consider some of the unique challenges and opportunities that there are in fabricating an analog circuit on an integrated circuit. So when we build an analog circuit on a single silicon die, we have some limitations and we have some advantages. A couple limitations. One is that we cannot have any large capacitors in our circuit. It takes up too much room, and capacitors are hard to fabricate on silicon. Things in the order of picofarads, tens of picofarads, maybe even 100 picofarads is doable, but I'll just say less than 100 picofarad, certainly less than a nanofarad. No large resistances either. It takes up too much real estate to fabricate large resistances. So I'm not sure on the value here. I'm going to say somewhere around minus 10K. This is just rule of thumb. I have to double check this. But it's going to motivate why we're looking at some of the things that we're looking at in this chapter. The transistor output resistance, which, if you recall, appears across the controlled current source. So if it's a MOSFET, then we have a drain, and we have a source, and there's an RO. That's across there. And that RO is small. It's small for modern IC fabrication. And so what that means is that we can't ignore it like we have for most of our amplifier analysis so far. We just kind of left it off, and usually the loading resistor, the collector side resistor or drain side resistor, was just the discrete resistance that was tied, that was in series with the drain or the collector. Here that's not the case. You can't ignore RO. So there's going to be efforts to increase the effective RO, because without a large RO, you're going to limit the voltage gain that you can achieve. Now, a couple positive things of IC fabrication are that you can have very accurate ratioing or scaling of devices. So we can, although we can't say that we want a transistor to have an exact transconductance coefficient Kn, we can say that we want transistor M2 to have transconductance coefficient that's 2.00 times that of transistor M1. That it can do very accurately. And then, in addition, some of the parameters of the devices, such as transconductance coefficient, threshold voltage, scaling current and forward current gain, etc., for if it was bipolar transistors, those can be well matched within on a given die. It's not that we can specify them with great accuracy or precision, but great accuracy, I should say. But from device to device, they will be consistent on a given silicon die. So we now will start looking at these 5 items, beginning with gain blocks. Now, the idea with the gain block is that we're trying to find out how large of a voltage gain can we achieve, knowing that the limiting factor is going to become this output resistance that we can no longer ignore. So let's begin first with our classic common source or common emitter amplifier stage, where the source in this case is grounded, and we have a pull-up resistor RD and VI and VO. Here we can say that the output will be, if we do small signal, just go ahead and put the small signal symbols there, that VO is minus RD times GM times VI. And what is GM? GM can be written in several ways. First, it can be expressed in terms of the operating drain current. That's 2 times Kn times ID, the operating current. That is also equal to Kn times the overdrive voltage, in other words, VGS minus V threshold. So I'll just write V overdrive. Okay. Now, if you recall that ID is equal to Kn over 2 V overdrive squared, this is in saturation. Okay, then we can take this Kn, plug it in there, and we can write that GM is equal to 2ID over VOD squared times VOD, and this leads to ID over VOD over 2. So we have this alternate expression here. We really have 3 expressions for GM. And we want to look at more closely at this last one. We see that VO is equal to minus RD times ID over VOD over 2. But then we recognize that RD times ID is just the voltage across our transistor, or across our resistor. So I'll call that VR. And of course there's a minus sign. So we'd say AV is equal to minus VR over VOD over 2. Now, if we were trying to maximize this this voltage gain, then we would want to, for a given operating point, we certainly would want to maximize VR. And in general, we would say, well, we want to maximize RD, and of course we want to maximize GM as well. Looking closer at this last term here, we would say that really what we want to do to increase gain is we want to increase the voltage across the resistor while decreasing the voltage across, or the overdrive voltage. Now, if we decrease the overdrive voltage, we're actually decreasing the drain current. And if we decrease the drain current while either holding VR constant or even more challenging, trying to have VR increase, then what that means is that RO, or our RD here, must increase. Now, we already stated that in IC fabrication, this output resistance RO cannot be ignored. So what we would have in each of these cases would be RD in parallel with RO. And so to increase the gain, what we really want to do is increase RD in parallel with R to RO. So we might say, well, okay, to maximize the voltage gain, set RD to infinity, right? So you have no resistance. Of course, that leads to a problem, because then you have this kind of circuit here with an open, the drain is open. You can't have any current flowing. This is impractical. So there's another approach. We can try this. What if we actually replaced the resistance RD with the current source? Now, current source has a dynamic resistance of infinity. And so we effectively have an infinite resistor, but we are providing a current path for biasing this transistor. We have RO, and now the voltage, I shouldn't put the small signal on here yet because I'm showing this bias current. But now we would say that AV, and we'll call it AVO here, because AVO being, this is the maximum gain you can achieve. In other words, we've increased this resistance as much as we can. We're down to whatever the transistor provides or limits us to. And we'll have AVO is equal to minus RO GM. Now, we can take this a little further, and we can write that AVO is RO times ID over this VOD over 2. But now we note that RO times ID is something that we've seen before. Let me draw a transistor output curve for a MOSFET. We have this family of curves, and ideally in the saturation region, which is right here, the current is independent of VDS. But the reality is that there is a finite slope, a non-zero slope. And I'm going to exaggerate it here. So the actual curve looks like this. Okay, and all of those curves cross back here or intersect the x-axis at a voltage of minus VA, where VA is the early voltage. It's called the early voltage. And what we see is that it turns out that the dynamic resistance, so this right here, 1 over, this has, the slope has units of current over volts, so it's conductance, and it's equal to 1 over RO. You see that RO is actually a function of the operating current. 1 over RO turns out to be, or RO turns out to be VA over ID, or RO times ID is equal to VA. And that can now be put to use over here, such that we have AVO is equal to minus VA over VO over 2. And this is the maximum gain that we can achieve for a MOSFET amplifier, MOS gain block. So it looks like infinity there. Let me fix that. That's overdrive. Now for modern IC fab, AVO, I'll say AVO FET. AVO FET, achievable AVO FET is in the range of 20 to 40 volts per volt. And the overdrive, typical overdrive voltages are in the range of 0.15 to 0.3 volts. So we can't achieve really high gains with modern IC fabricated MOSFETs. Now, before we go further, and we'll look at the BJT version here, I just want to point out that if you tried to build this amplifier stage here discretely, just by itself, you would have a terrible time of ever getting this to find an operating point. In fact, you wouldn't likely be able to do it. And the reason is that RO is so large. Well, the drain current ID times RO is a voltage that is very sensitive to RO, and there's no regulating or negative feedback mechanism like we saw when we put a source resistor in our, say, common emitter amplifier stage. And so this type of amplifier is intended to be used in a larger amplifier where there's negative feedback. In other words, a portion of the output comes back and will adjust the input signal, the signal that is being fed in here is VI, so as in such a direction as to tend to stabilize V out, or that drain voltage, to an operating point that is somewhere between 0 and VDD. So we're kind of taking this gain block out of a larger system, and you shouldn't think of it as something that would work on its own. Now, before we go any further, I should point out that if you try to go in the lab and build this stage right here with the current source in the drain, you'll have a difficult time getting this to be biased up to an operating point that keeps the device in saturation. This is not to be thought of as being used by itself, but rather being an amplifier stage that's with part of a larger amplifier system in which there is negative feedback. Now, there's one way that you could get this circuit to work in the lab discretely, and let me draw that here briefly. And so this could be tried out. I mean, this could be explored, if you will. So if you have a current source, and in order to bias this, what we might be able to do, what we could do, is to add in this gate resistance, and let's make it really large. Let's say that you made it 1 mega ohm. Okay, and so what you'd have is that this voltage here, VD, operating voltage, the operating point, is going to be equal to VGS because of how this is tied together, right? There's no current flowing from the drain or into the gate. And so VD is equal to VGS, which is equal to V threshold plus the square root of 2ID over Kn. Okay, so that would be your bias point. And really what this is doing, this RG is employing negative feedback, right? Negative feedback, because if the current of the transistor, if the channel current decreases, more current of this, more of the ID current will go through RO, thereby raising the drain voltage. And if the drain voltage rises, then the gate voltage rises, which then tends to turn the transistor on, which then diverts the current I, the current source current, back through the channel. So actually, I shouldn't call this ID. That's really not a good thing to do, because it is not exactly the drain current, right? It is, this current splits between the channel, the drain current, and that RO, whatever current path is afforded by the resistance RO. Okay. So what we've looked at so far is the MOSFET gain block, and we've seen that the maximum achievable gain is VA over VOD over 0.2, and for modern IC fabrication, there's a limit to 20 to 40 volts per volt, and VOD is in the range of 0.15 to 0.3 volts. Another point that should be made about AVO for the FETs is that there are diminishing returns at low ID. Okay, diminishing returns at low ID due to sub-threshold IV behavior. So our model for the transistor in the saturation region kind of breaks down when we get below the threshold. So where did I write that? Where did I write that relationship? Right here. This guy. This breaks down at sub-threshold voltages. So in other words, we are limited in the maximum gain that we can achieve with the MOSFET gain block. Now let's look at a bipolar gain block. So for the bipolar gain block, we have a similar situation where we also have RO, and here we're going to go straight to looking at how we can maximize the gain. So we're not going to have any collector resistance. We're just going to have this current source. I'll go ahead and draw RO as an external to the transistor, though you understand it's part of the transistor. And we have VO at the collector there. And again, we have VO is going to, small signal VO is minus RO times GM times VI. GM for the bipolar transistor is, this is amps per volt, and so we have IC, the collector current, divided by the thermal voltage VT. So if we plug this in, we get that AVO for the BJT is equal to minus ROIC over VT. And this, as shown before, for the MOSFET, we have a similar case here that this is equal to the early voltage. So in other words, for the bipolar junction transistor, the gain block, achievable gain for the gain block is VA over V thermal. For modern IC fabrication, VA is in the range of 5 to, what is this, 5 to 125 volts? That seems large. No, 5 to 35. 5 to 35 volts. For old high voltage, what's so-called high voltage fab. This doesn't mean it's archaic or old, it just means it's not what's being used for the modern ICs where they're trying to pack as much as they can on a die. There's still many uses for high voltage fabrication, both for integrated circuits and as well as for discrete circuits. Here VA is in the range of 100 to 130 volts. So, and recall that the thermal voltage is equal to 25 millivolts, or 1/40th of a volt at room temp. So therefore, AVO of the BJT is going to be in the range of, let's see, 5 to, let's see, what is this? So it'll be 2. Yeah, so it's going to be 40 times 5 to 35 volts for the modern fab, and between 100 and 130 for the older fab. So this is approximately 200. Well, the overall is going to be between 200 to 5,000 volts per volt. And clearly the higher gain is going to be achievable with the older, the high voltage fabrication. Notice that the gain does not depend on the current. Okay, so BJT gain not dependent on IC. So that's important. And of course, we note that there's a higher gain, higher achievable gain with BJTs over FETs. And again, if we wanted to build one of these, it has to be within a feedback system. So one way we might be able to do this, if we were going to build it discretely, would be as follows. So we would have, in general, some kind of a resistor network that would connect from the collector back to the base. But these two resistors, RB1 and RB2, we would want these to be much larger than RO, or they would actually influence the achievable voltage gain. This is not typically what's going to be done in an actual integrated an IC amplifier, but if you wanted to do a single stage demo, this might work.